So, let's see, what would be a good example? Whenever you have, if somebody says, of course you've heard of carbon-14 dating, let's pick on that. Carbon-14, okay? So the symbol for carbon is C, and actually if somebody says 14, what they're saying is that that is what we call the mass number. The mass number, okay? I know that, or atomic mass number, I have two different books that do it differently. But the mass number is equal to always the number of protons plus the number of neutrons. Okay, and when we talked about an atom, the protons and neutrons are located in the center of an atom, in the nucleus. So honestly, in this example, they're saying I have a carbon atom, and in the nucleus, that's that big circle there, okay, if I count up protons and neutrons, they equal 14. Now here's the problem. Well, it's not really a problem, but carbon, the protons are set in stone. The protons for carbon are set in stone. So for instance, carbon, you guys are going to have a periodic table for your test. Carbon must have 6 protons in its center because it's got a 6 there, right? That's actually its atomic number. So we know it has 6 protons. Okay, 6 protons. Now, do you see where, in this example, if it has 6 protons, how many neutrons must it have to equal 14? Not 6. 8, exactly. I'm going to go ahead and make little zeros for my neutrons. 2, 3, 4, 5, 6, 7, 8. Okay, so that's that particular carbon atom. It's got to have 6 protons, and in this case, its mass number, so mass numbers are a whole number, and it's the number of protons, which is set in stone 6. The number of neutrons can kind of vary, okay? So in this case, yep, it's 8. Okay, so I kind of did it backwards what you guys were doing for your homework. Are there any questions about that? What's that?
Can you leave it up for a second?
Yeah, I'll leave it up for a second. While we're at it, I want to kind of remind you one other thing we talked about. We said that elements, okay, so if you look in the center of an atom, you know what element it is because of the number of protons. But here's the deal. They're called isotopes. Okay, remember your exams in here have like a vocabulary section, and that's a good word to put on vocabulary, right? Isotopes, okay, they are the same element, but they have different numbers of neutrons. So let's go ahead and take carbon as an example. There actually is a carbon-13, and there is a carbon-12. Okay? So that just means that they have mass number of 14, mass number of 13, and mass number of 12. Okay? So can you see where in each of these cases, and it's kind of a little off, but in this case over here, for the carbon-13, if I were going to write number of protons, how many number of protons? 6, exactly. Plus question mark is equal to 13. How many neutrons are in a carbon-13? 7, exactly. That's it. There are 7. Let's do the last one. Okay, so carbon-12. Anytime you see like a number after the symbol like that, that's its mass number. That's its, in its nucleus, protons, which we know, and neutrons, which can vary. So here, carbon-12, against, we still have, what, 6 protons, and it's equal to 12. So how many neutrons do we have? 6 also, yep. That's exactly it. 6 neutrons, 7 neutrons, and 8 neutrons. And it's kind of cool because they actually have like scientific equipment that can detect the differences in those masses. Okay, so that's kind of cool. All right? So that's that. They're called isotopes. Well, we spent, I'm anxious to kind of see how the whole we call it nomenclature, when you name compounds. okay? I'm anxious to kind of see how that went. So now I want to switch gears and go to talking not about ionic compounds, but I want to talk about the other ones. So the other ones are molecular compounds. Remember, we have molecular compounds and ionic compounds. Molecular compounds. So molecular compounds, the deal is you don't have a metal, basically. Molecular compounds, you don't have a metal. And when we go to look at how that compound is arranged, we're going to actually see all of those bonds are covalent bonds. Okay, all of those bonds are created by electrons being shared. No ions there. No metals, no ions in a covalent or molecular compound. And remember we said that, like in the example of your homework, you were supposed to tell me, I'd give you the formula of a compound, you say which category it falls into, and I said look for the metal, and if you find the metal, it's an ionic compound. Okay. No metal, not an ionic compound. Hydrogen is a nonmetal. So we're not going to have you draw your Lewis structures, but I want you to be able to kind of look at a Lewis structure. All a Lewis structure is basically shows you all the atoms and kind of how they're laid out to make the compound, okay? In some of my other classes, we actually make the Lewis structures, or simple Lewis structures. So anytime when you see these Lewis structures, anytime you see a dash, that's actually connecting the atoms together with a chemical bond, kind of like we've been talking about already. But now you know that electrons not transferred, electrons shared with that little dash connecting those two atoms. So one of the things, although I'm not going to have you draw your own Lewis structures from scratch, I want you to be able to identify what's called the pot of valence electrons. Now, we've talked about valence electrons in here, right? We said that if you want to know down around an atom how many of those electrons are valence electrons, you look at the group number, right? Okay, so basically I'm just going to kind of have you, and sometimes I use a calculator, to go ahead and just kind of add up, given a collection of atoms, how many valence electrons do they all total bring. Okay, so you're going to add them all up. It's kind of like when you guys did your molecular weights. You added up the weights, the pot of valence electrons, you add up all the valence electrons, okay? That's the pot. I was thinking pot of gold, pot of valence electrons. Okay. So when you see I'll show you a couple of Lewis structures here, I think. I didn't know where to put them. But here are a couple of Lewis structures. Like when you look at different elements that kind of bond together to make compounds that are important to us, of course, carbon's very important. And carbon makes a lot of different things with hydrogen. So I'm going to pick on carbon and hydrogen. So we have a few compounds. We have this one. Let's see. C2H6. C2H6. It's got 2 carbons and 6 hydrogens. Okay. So one of its configurations look like this. Okay, I put a carbon, bond, carbon. And then I got to put my hydrogen somewhere. So actually I'm going to put 3 hydrogens around each one. So from this carbon, and usually I'm going to go north, south, west. Okay, north, south, west. I'm going to do a little knob, which is going to be my chemical bond. And here go my 3 hydrogens. And it's a very symmetrical, these ones I'm picking on that I want to show you, these are all very symmetrical. So we're going to do the same thing with the right carbon. Okay, so that is what we call a Lewis structure. That shows what the 8 atoms, kind of how they're arranged, right? Each of these bonds, each of these dashes right here is a chemical bond. Now, this talks about bond pairs. When you think of pairs, do you think of 2? I do. Okay, so actually where it says bond pairs, you can think of 2, specifically 2 electrons. So one of the things I want you to get in the habit of just this morning is anytime you see a dash there, think 2 electrons. So let's go ahead and count electrons. Let's see, I got 1, 2, 3, 4, 5, 6, 7. 7 bonds. 7 times 2 is 14. 14 electrons. Does that sound okay? I think so too. So it's 14 electrons on that structure. Now, let's look at the pot of valence electrons. So when I do a pot of valence electrons, it looks like this. I'll say the element, which is carbon. Okay, element, which is carbon. How many there are, which is 2. Okay, and then I will multiply it by how many valence electrons each carbon atom brings. Valence electrons. All right, so now here's where we need a periodic table. So carbon is 4A, so it brings 4, each of them bring 4 valence electrons. So here we go, 4 electrons right there. Bada boom. So I got that from the group number. All right. So then if I have 2 carbons, each of them bring 4 valence electrons, I have a total of 8 valence electrons from carbon. Seem okay? 8 electrons. And then I do the same thing for the other thing, okay, that's present, which of course is hydrogen. So I'll put a hydrogen, colon, there are 6 of them, so I'll put the number 6. And then I'll go to the periodic table to see how many valence electrons each hydrogen brings. It's 1A, it brings 1 valence electron each. You figure a hydrogen is like the simplest element there is, so it has 1 proton and 1 electron, and that 1 electron is a valence electron. Okay, so 6 times 1, okay, is equal to 6. Okay, so now in some examples, and actually the example I'm going to send you home to turn in on Wednesday, this is the pot of valence electrons I want you to come up with based upon what? The formula? Okay, this is based on the formula. Okay, whereas this number over here that we got, this red 14, this is based upon the structure. Does that make sense? And my only point here is, of course, if we add 8 plus 6, I don't need a calculator, sometimes I do. Okay, you do get 14 electrons. Those two numbers should match. The number of electrons you see on the structure compared to the number of electrons that come from the formula, from the pot of valence electrons. They should match, and they do, which is wonderful. Yes?
Okay, so it says on the body electron pairs, we multiplied it by 2, the 7 by 2 here, 7 bonds by 2. Do we need to multiply it by 3 for the triple bonds? Or is that just...
I'm coming up to an example for that. Actually, for the double bond, each line is going to be 2 electrons. So a double bond actually is going to be 2 plus 2 or 4 electrons. So I have an example of that coming up.
So that was a single.
Those were all single.
Okay.
Very good. Those are all single. You got it. These are all single bonds. You got it. So I'm hoping there's enough room at the top there because I don't want to go on to the next slide. At the top there, I'm going to do the next example. So the formula for the other one, or another one I want to do, is also got 2 carbons. So it's C2H4. And we're going to do, I'll show you what, I'll give you the structure. Okay. So for C2H4, here we go. We have a carbon bonded to another carbon. But actually, this is what Cammie was saying. In this case, notice I'm going to make it a double bond. I have carbon with 2 lines. That is what we call a double bond. The abbreviation for double, does it sound okay? DBL, double bond. Okay, let's finish this. I'm going to show you the Lewis structure, and then it's very symmetrical again. Not all molecules are symmetrical, but I'm going to put 2 hydrogens on one side, okay, and 2 hydrogens on another side. Let's go ahead then. Now, this actually is a good example. Each dash is 2 electrons. So can you see where if I have 2 electrons here, and actually 2 electrons here, every double bond is 4 electrons. And it really is. It totally really is. Every double bond is 4 electrons. 4 electrons. So 2 electrons for the first dash, 2 electrons for the second dash. If you have a carbon with 3 dashes between it and another carbon, how many electrons you got there? You have 6 electrons there. And that's called a triple bond. And you feel the energy in a triple bond. That would be true. So if we're counting electrons, I got to count that double bond as 4 electrons. Let's do it this way. I got 4, and then I'll add this, be another. 4 plus 2 is 6. 6 plus 2 is 8. 8 plus 2 is 10. 10 plus 2 is 12. So I got 12 electrons. That's cool. I got 12 electrons on the structure. And let's go ahead, and I'll change it to my green color. And so up here, let's go ahead and come up with the pot of valence electrons. So carbon, there are again 2 carbon atoms with the number 2 there. They're 4A, so there are 4 valence electrons for each. So collectively, there are 8 valence electrons for carbon. For the hydrogen, there are only 4 hydrogens here. Again, each hydrogen is 1 valence electron for a total of 4 electrons from hydrogen. My pot of valence electrons is 12. 12 electrons. So here's where we can compare the structure with the pot. Okay, so structure is 12 electrons. The pot is also 12 electrons. We good with that? I think I can. Let's see. Well, let me do that. Can I erase that for now? Okay. Oh, I've never done that before. Okay. Let's go ahead and do I have another analogous compound, and the formula for this third compound is again C2, but now instead of 6 or 4 hydrogens, it's only going to have 2 hydrogens, C2H2. And I'll give you the Lewis structure. So again, the carbons are bonded together, but now instead of a double bond, actually it's a triple bond. Carbon with 3 dashes and another carbon. And then we're going to put the hydrogen on the left and the hydrogen on the right. So anytime you see a Lewis structure, each dash is a pair of electrons. So I got, for the triple bond, like you guys were saying, I'm thinking 6 electrons. How about you? Okay, and then I got 2, 6 plus 2 is 8, and then I got another 2, I got 8 plus 2 is 10. So I got a total of 10 electrons on the structure. So now go ahead and let's come up with the pot of electrons. We'll do it in green. With regard to carbon, carbon, there are 2 carbon atoms. They each bring 4 valence electrons, again for a total of 8 valence electrons from carbon, like it was all the other 2 compounds. For hydrogen, there are only 2 hydrogens. They each bring 1 valence electron. And so collectively, hydrogen is 2 valence electrons. If I add up my pot, 8 plus 2 is 10. So that's it. So of course, they match. But I haven't even said the coolest or most important thing about this. When somebody draws an appropriate Lewis structure like these have been, okay, it ends up that, I'm going to go ahead and go back to the C2H6. Here's our C2H6. So carbon, single bond carbon, and then 3 hydrogens scattering off of each carbon. Remember we talked about something called an octet? Or I think we might have said 8. Octet. 8 electrons. We said actually that's kind of why ions form in the first place. They want to get an octet. Okay? Either the nonmetals gain electrons to get an octet, or the metals lose electrons to get an octet. Well, here's the deal. If we look around carbon, let's pick on carbon. Can you see where, as I draw this circle to include those bonds for this particular carbon, the bond to the hydrogens and the bond to the carbon, and if each of those are 2 electrons, I have 2, 4, 6, 8. I have 8 electrons around that carbon atom. That is your octet. Okay, so actually there are 8 electrons being shared. And then let's go ahead and jump to the triple bond, acetylene. So if we have hydrogen, bond, carbon, triple bond, carbon, bond, hydrogen. And go ahead and draw a circle around the left carbon. Actually, the number of electrons around there, I got 2, 4, 6, 8. I have 8 electrons around that carbon atom. 8 electrons are shared. So that's awesome. There's your octet. Okay. So now this line right here, you guys might need to go ahead and get this in there. Actually, I added this morning. It really should have been in my original notes that were printed. This slide talks about valence. Okay, valence. Now, valence is different than valence electrons. I wish they would have come up with a different name. I know that they're related, but I wish they would have come up with a different name. Valence, the valence of an atom is the number of covalent bonds it will form. Ugh. Okay? The valence of an atom is the number of covalent bonds it will form. We've been looking at Lewis structures of compounds a minute ago, like Lewis structures of molecules. These are actually like simple Lewis sort of structures of just the atom. Okay? Do you see where carbon we said is 4A? Those are the 4 valence electrons around a carbon atom. Nitrogen is 5A. Those are the 5 valence electrons around a nitrogen atom. Oxygen 6A, fluorine 7A, and neon is 8A. Can you kind of see where these, actually neon and all of its buddies, all the rare gases already have 8 electrons around them? So they're like, I'm done. Okay. But if we look at the number of valence, expected valence for an atom, and this didn't make it in my slides this way. What I usually tell students, and it works pretty darn good, is you can calculate valence of an element by taking the group number, I told you wrong, by taking the number 8 minus the group number. Final answer, 8 minus the group number. So above carbon, we could do 8 minus 4, right? 8 minus 4. So the valence is 4. Above nitrogen, we could do, 8 minus 5 because it's 5A. So 3 is the valence for nitrogen. For oxygen, it's 8 minus 6. That's equal to 2. The number of covalent bonds that oxygen forms is 2. And for fluorine, it's 8 minus 7 because it's 7A. So it, sometimes I say reaches out. It forms 1 covalent bond. And of course, neon is 8 minus 8, which is 0. Okay, so it doesn't form any bonds. So again, if we look back, let's see, I didn't see what my next slide is. Okay. The valence of hydrogen is always 1, if you want to jot that down. Valence of the element hydrogen, if hydrogen isn't, it's going to only reach out once. Okay? So in all those structures, I'm not going to draw them again, but those 3 carbon structures we looked at this morning already, if you look at carbon and kind of look around carbon, notice that in each of those cases, it has 4 bonds. So it is actually doing what it should. All right, so Lewis structures. So when I drew those Lewis structures this morning, when I drew the C for carbon, think of anytime you see the symbol for an element is basically representing its nucleus and all of its like inner electrons, not the valence electrons, because those make up the bonds. Okay, so that's what that is. We talked about bond pairs. Okay, we talked about the fact that bond pairs, okay, that you see 2 electrons for every dash. If you have 1 dash, of course, that's a single bond. If you have 2 dashes, that was what, 4 electrons? Okay, that was a double bond. If you see 3 dashes, that's 6 electrons, and that's a triple bond. One more thing I need to talk about. Sometimes electrons actually end up as what are called lone pair electrons. And I'm going to show you some examples of that. Actually, I'll go ahead and do a Lewis structure over here of water. And you're going to see actually the oxygen ends up with lone pair electrons. So here we go. If in my other classes, if I was going to have students draw a water molecule, I actually would have them come up with the pot of valence electrons first. So let's go ahead and do that. H2O, the element hydrogen. There are 2 hydrogen atoms. Each of them bring 1 valence electron. So we have 2 electrons coming from those 2 hydrogens. For the element oxygen, there's only 1 oxygen atom. It is a 6A element, so it brings 6 valence electrons. Okay, 6 valence electrons. So my pot is 8. 8 electrons.
Oh, never mind, never mind.
Yeah, good. Because sometimes, yeah, it is 8.
I wasn't looking at your 40.
So you probably figure right off the bat, you're like, well, I think there must be a center oxygen, you're right, and 2 hydrogens branching off of the oxygen, and you're right. That is very cool. But do you see where if I go ahead in this structure, if I count electrons, I'd be like, I see 2, 4. I only see 4 electrons there. So something's not quite right. Not only that, but I only see 4 electrons in that Lewis structure, and if I circle the oxygen and count electrons, I only have 4 electrons around it, and it wants 8. So here's the deal, and again, I'm not going to necessarily make you draw them this semester, but those other 2 electrons end up looking like little antennae, like little, okay, those are lone pair electrons. So I'm going to redraw this Lewis structure. So actually the Lewis structure for water looks like this. Dot, dot, and they always come in pairs, or the ones we look at come in pairs anyway. See this dot, dot, dot? Sorry, this dot, dot. Got carried away. This is actually a lone pair electron. Oops. I'll show you what a water molecule looks like. So water molecule looks like this. Okay, so the black here is oxygen, and then this is a hydrogen, and this is a hydrogen. So oxygen, hydrogen, hydrogen. So these are the bonding pairs. Okay, so we have 2 electrons here, 2 electrons here, and then these are the lone pair electrons, which is awesome because they actually they need space to wiggle. Actually, they're wiggling out here. They're like 2 antennae. Okay, and this one's wiggling over here. 2 electrons over here, lone pair electrons, 2 electrons over here. So that's actually why when we look at a water molecule, it's not straight across. A water molecule is not like this. Because those lone pair electrons actually squish them down. It bends the molecule. This is what a water molecule looks like. And the visible lone pair electrons make it past you. Isn't that so cool? And your textbook goes into kind of looking at Lewis structure and understanding what shape the molecule is. Okay. All right. So kind of like you saw there with the water molecule, Lewis structures are like paper and pencil sort of things. You can take your models and kind of fluff them out to get a sense for what the overall shape of the molecule is. The shape of molecules is a player in how they react and how they don't react. And so, all right. So we have a few slides here to kind of do together. So this is ammonia, and I brought these today because I thought this would work out. I only have these because these work the best. Okay, so you guys are actually, we're going to look at it, answer some questions, and then you guys are going to make how about, let's see, Cassie, we'll have you kind of come up and, there's plenty. So you can kind of share with them, and then you guys can kind of share with them. So you're going to need some, I'll get you Cassie what you need. You're going to need some things to represent the nitrogen and some things to represent the hydrogen. And I'm hoping everybody can do it. So let me give you, let's make yellows the hydrogen. And I'll give the box to them, and I think I got you enough. So pick any color. Here, look. Did I give you a box yet? So, pick any color. Guys, got to do that. Got to do one first. Any color, the central nitrogen atom, and then do the bond and the three hydrogens. And don't forget the lone pair electrons. So it should be enough for everybody to do. And then, on the test ones, you should do it all like this. I don't say this to them. Isn't that adorable? Awesome sauce. So one of these represents hydrogen and three hydrogens.
Okay, so hydrogen just because it has those three boxes, I get a word.
And then these would be the three?
And then those connectors.
Oh, those connectors.
Yep, those connectors.
Like so.
Yeah. Cool. Heck yeah.
That would be like that.
Yeah, exactly. And then all I'm trying to do is you put one more loop on there.
Yeah, I always do
It's like Christmas. Still look like ammonia? Awesome. And then, this, it's one more to match up.
Oh, okay, that makes sense.
Because it makes space around it.
There we go. Now
Yeah.
it's over there.
Yay. What do you think? So let's go ahead and confirm the pot of valence electrons. I think some of you already done that. So let's see. We have nitrogen. There's one nitrogen. We have to look at the group number. It's actually 5A. So it brings 5 valence electrons. And there are, so total of 5. And with regard to hydrogen, there are 3 hydrogens. They each bring 1 valence electron for a total of 3 valence electrons. You add those two together, and you got 8 electrons that are on the pot. So that's from the formula. And then actually, let's see. Oh, I said confirm. So let's go ahead and go to our structure. I got 2, 4, 6, 8. I do have 8 electrons. Does everybody buy that? That's all I wanted there. Structure. Does each atom have a complete octet or duet? So here's where you take nitrogen and you draw a circle around nitrogen. Well, you don't, in your mind or in the paper if you want. But as I draw a circle around nitrogen, notice that it actually has 2, 4, 6, 8. It does have 8 electrons. Okay? So I see 8 electrons around nitrogen. And I said duet because actually hydrogen, what element has 2 electrons around it in its neutral form? What element has 2 electrons around it in its neutral form? Because if it has 2 electrons in its neutral, it must have 2 protons. What element has 2 protons? You guys know. Helium, right? Okay. So helium actually has two protons. Helium is a rare gas. So that's why actually when it says or duet, okay, duet means actually this, we do have 2 electrons around each one of these hydrogens. Okay, so it is. It's awesome. So I say yes. Yes. And then one last kind of miscellaneous question. Now, how many pairs of lone pair electrons are there? Hold up your fingers. 1. 1 pair. I'm liking it. Not all structures have, but this one does. All right. Good job. Let's go to the next one. Dun, dun, dun. Okay, so go ahead and make this structure. You'll need 3 little balls representing carbon in the middle, oxygen, and 2 hydrogens. And with that double bond, my hint is you can't break them. You can't break. So basically, you're going to take white things and kind of between your carbon and oxygen, you're actually going to have 2 white things going between your carbon and oxygen. Because that's what the end does. Yep. Well, no,
Because you have to have 2 hanging off the side like freaking.
No, because they aren't there.
Because
No,
you
you
have
don't.
the secret ones.
But it'll work. Don't forget your lone pair electrons on the oxygen.
Crack cocaine.
Yep.
Good. I'm keeping it like that.
Okay.
I pass. I know. Because they have the 2 long ones.
So, like this one, if you make these so we can make a double bond between your carbon and oxygen. So you need that one, yep, you need that one, you need one more. Break. Yep.
Mine is right. I don't care what you say, it's right.
That'll work. Okay, so this actually, what I'm trying to, you guys came up with something that looks kind of like this. I walked around. Okay, so you basically had to have two white things between your carbon and your hydrogen. And if you squish those down, okay, can you see actually where you end up with kind of a triangular shape? okay, if you squish down, okay. So that triangular shape actually is what we call trigonal planar, that triangle shape. All right, so let's do some counting. So coming up with our pot of valence electrons first, there are 2 hydrogens. I usually just kind of go with how the formula is. So there are 2 hydrogens. With regard to hydrogen, there are 2 of them, and of course they each bring 1 electron each for a total of 2 electrons. Then we're going to go to carbon. There's 1 carbon atom. Again, carbon is 4A, so it brings 4 valence electrons for a total of 4. And then we go on to the oxygen. There is 1 oxygen atom. It's a 6A element, so it brings 6 valence electrons. So when I add 2 plus 4 plus 6, I get 12. And let's double check that actually on our Lewis structure we have 12. So I'm going to count in twosies. So I'm going to go 2, 4, 6, 8, 10, 12. Okay, so I do have 12 on the structure. All right. So let's do a little bit of circling here. Let's circle the carbon atom and see if we have an octet or 8 around the carbon atom. And I'm liking it. I got 2, 4, 6, 8 around the carbon atom. Let's circle the oxygen atom, see if we have 8 around the oxygen atom. I have 2, 4, 6, 8. I know it's getting kind of busy, but yes, I have 8 around both of those. 8 shared electrons around both of those. Of course, hydrogen is just a duet. So I say yes. And fingers, please. How many pairs of lone pair electrons are there now? 2. All right. Un mas. Ah, triple bond. Oh, yes. Okay, so you'll need 4 atoms to join together this way. And I've only had just a few times when they break, but you know, plastic doesn't stick around forever. So. See some of you working on it, so I'm going to go ahead and work on it too. The pot of valence electrons. For the carbon, there are 2 carbons. They each bring 4 valence electrons for a total of 8 valence electrons. With regard to hydrogen, this seems familiar. There are 2 hydrogens. They each bring 1 valence electron, so 2 valence electrons there. Our pot, according to the formula, is 10 electrons. On the structure, if we count electrons, I got 2, 4, 6, 8. 10. Actually, I got 10 electrons on the structure. And that's what I mean by confirm that those are the same. So does each atom have, well, it's very symmetrical. Does each atom have a complete set of 8 electrons? So I'm going to take this left carbon and I'm going to put a circle around everything that's connecting it. And I'm going to count electrons. And I got 8 electrons around that carbon atom. And the right one would be the same. Okay, and the hydrogen is a duet. So I'm going to say yes. Yes, 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 yes. And then hands, please. How many valence how many lone pair electrons are there? No. Very good. There are 0. Okay. Now one last thing. If you take that triple bond and you squish it together, does it kind of flatten out like this? Okay. Actually, the shape around each one of those carbons is what we call linear. I call it hot dog shape. So that would give you the shape. Okay, so I couldn't find an assignment in your textbook that I like. Oh, we do have one more. Okay, we aren't going to do the Lewis structure of this one, okay? But we are going to do the pot of valence electrons. We do have one more. So you do it and I do it. I'm going to go with carbon first. There are 1, 2, 3, 4, 5 carbons. Okay. And so carbon is 4A, so 5 times 4 electrons for 20. Ooh, I might need to get my calculator out for this. And I'm going to go with hydrogens next. Wouldn't have to, but so I'm counting 1, 2, 3, 4, 5 hydrogens, and they each have 1 valence electron for collectively 5 valence electrons. And then I'm going to go with oxygen next. There's only 1 oxygen atom, and it's a 6A element, so 6 valence electrons there. So I have 6 electrons brought by oxygen. Then I have a nitrogen, believe it or not. So I have nitrogen, only 1 of them. Nitrogen is a 5A element, so it brings 5 valence electrons. All right, so it looks like, see, 5 plus 5 is 10. Plus 20 is 30, so I'm getting 36. Does that seem right? So a total of 36 electrons from the formula. So let's count. I'm going to just do checks. I'm going to count checks, and each check is going to be 2. Okay, so here are my checks. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18. So I have 18 pairs. Okay, and 18 pairs is 36 electrons on the structure. So, yep, it matches with our formula. Yay! And I'm not going to go through each one of these, but I will say yes, they do have complete octet. Now, in your homework, one of them is actually, for the homework I'm going to give you, something doesn't have a complete octet. So hands, please. Let's see. How many pairs of lone pair electrons? 3. 1, 2, 3. Those were hiding up here. 1, 2, 3. Perfect. Oh, yeah. Okay, so put your atoms away, and here is your homework that is due. That was the last slide, right? All right. So here's your homework that's due for Wednesday.
Yeah, we did.
Oh, gosh, awesome. And one of these you're going to see actually has an issue when it comes to the pot valence electrons and each atom.